MIPS architecture. Let's start with part D.1, basic properties of MIPS architecture. Yeah. All right. Let's start with addressing modes for MIPS data transfers. We have learned all the possible addressing modes. 6, right? Yeah. But for the MIPS, we only select 3 of them. The first 3, top 3. Yeah. But here, when we talk about addressing modes for MIPS data transfer, because among those 3, only 2 of them related to the data transfer. The third one is not related to the data transfer. So we separate. Yeah. So we separate 2 parts. Yeah. All right. The first part related to the data transfer. So the only data addressing modes here, let's look at this. Yeah. Immediate field. Immediate. Yeah. So here, remember, we have addressing mode, we call it immediate mode, right? Yeah. Immediate mode, but for the immediate mode, think about what kind of instructions do we use the immediate mode, right? Yeah. So let me use example here. Add R2, R1, immediate field, constant number 4. Yeah, for example, this one. So this one we use the immediate addressing mode, right? Yeah. But this one is not related to the data addressing mode, right? Yeah. Data, when we talk about data, we need to go to memory. When we talk about data, we need to, get to memory to get data. But here we do not need to go to memory, right? Yeah. So we get data either from the constant encoded inside instruction or from register, just one register. The register contains the data, yeah, like that. Yeah. But why I put the immediate field here? Because for the next one, the displacement mode, these two from the pattern, yeah, here I talk about the pattern of instruction. From the pattern, they are closely related. So that's why we put them together. Yeah. 2 different addressing modes, immediate mode, displacement mode, they are different. The first one is not related to data transfer, but the second one is related to the data transfer, but they share the same pattern. So we need to separate these 2 addressing modes. Yeah, so that's why we put them together, and we need to, use a special way to separate them. Yeah, here, both with 16-bit field in the 32-bit instruction. So we know for the MIPS architecture, each instruction has 32-bit long. But for the immediate mode or displacement mode, we use the last 16 bits as the immediate field. Yeah, we call it immediate field. We give a name called immediate field, but it can also be used as displacement. Displacement. Yeah, here. Yeah, here could be a little confusing. Here I use a term called immediate field. Immediate field. Inside that instruction, the last 16-bit. Later, when we look at the specific instructions, we will see that clearly. Yeah. So here I just, try to separate 2 concepts. The immediate field, you can store the constant, right? So you can store constant. Constant for operand operand constant. Yeah, operand. But you can also store displacement. So here you can see that's what we call immediate field. Okay, yeah. We do not call displacement field. We do not have any field called a displacement field. No such concept. We only have immediate field. But the number stored in the immediate field can be used in two different ways. The first way, constant operand in this type of instructions. Second, displacement number used in load and store instructions. Load and store. This D means double, okay? Double word. Yeah, later we will, because by default, our data in double words. Yeah. All right. Okay. Yeah. So here you can see, we spend a lot of time trying to explain this. Here, how about the register mode? Here, the register mode, because register mode, we will use a different type of instruction. Instruction type are different. So that's why from the higher level, they can be separated. From the higher level, they can be separate. So these two, the same type. Yeah, these two, same type. And later we will see, we call the I type. I type. Yeah. Why I type? I, immediate mode, right? Immediate mode, I. Yeah. This one, later we will see, we call R type. Why R? Because register mode, right? Yeah. So these two completely different types of instructions. So we can separate them easily. Yeah. So that means we do not need a specific bit to separate them. So these two, we need some specific way to separate them. Yeah. All right. Yeah. So let's go to the next. So example, let's look at an example. From this example, you can see, the difference easily. The first one, DADD IU R1 R2 pound 3. Yeah. Here, let me explain the meaning. D, double word. D, double word. Okay. Yeah. ADD, addition. All right. I, immediate mode. I type. Yeah, I type. Okay, immediate mode, I type. Yeah. U, unsigned. Yeah. So this operand, this number, we use unsigned representation so that we can represent the number in larger range. We do not need to use one bit for the sign bit, so we can represent larger range. Yeah. So that's the first example. Yeah. Second example, load. This time we use displacement. So immediate field is used as displacement 32. Yeah. LD, load double word. Yeah. R1 destination. Yeah. So the data load, after it is loaded, we put it in our destination field, R1. Yeah. Register R1. That's the destination. Yeah. Here, yeah. So then 32, displacement mode. With respect to base address, remember base address, when we talk about addressing mode, so base address stored in R2, so that's the meaning, The next one, DADD, this time we use the register mode, DADD U, this time we do not use I because this is R type. R type. Okay? Yeah. So no I. U, unsigned. Still, we use the unsigned integer representation. Yeah. All right, so that's these examples. Yeah. Next, MIPS. It has this property, byte addressable. So in main memory, every time when we use a different address, that means that corresponds to a byte, not bit, not bit, too small, too small. So for a bit, there is no address corresponding to a bit. The smallest unit, so the byte addressable, this byte is the smallest unit with an address. And that is a byte. Okay, that is the byte. Okay, yeah. So we call it byte addressable. That's a property. Next property, all right. MIPS memory is byte addressable. Yeah, repeat the previous one with a 64-bit address. Yeah, so here we are talking about MIPS 64. Yeah. If we do not use that number by default, we mean MIPS 64. Okay, yeah, because that's the most popular, the currently used MIPS architecture, MIPS 64. Yeah. Byte addressable with 64-bit address space, 64-bit. Yeah. So each data has 64-bit, double word. So that's a double word. Yeah. Naturally, double word. Yeah. All right. So next topic, memory accesses for MIPS. So let's look at that. Now we need to look at how to access memory. Yeah. Types of control flow. Yeah. All right. Yeah. First, let's look at the control a little bit. Yeah. Control a little bit. Yeah. First, conditional branches. If statement. Think about while loop, for loop, all those types of instructions, conditional branches. Later we will see more details. Yeah. Another type, jump. Okay, yeah. And all these instructions, actually, we need to specify some address information. So that's why, memory addresses. So these, let me give you all the possibilities. So then I talk about, related to the memory address part. Yeah. Next one, procedure call. Yeah. Function, procedure, you call a function, procedure calls. Okay. Yeah. Another one, procedure returns. Yeah. After your function complete, some specific task, you need to send control flow back to the original instruction flow or original instruction sequence at the right point. So that's the return part. Yeah. All these things you need to change. So all these things you need to change the control flow. Okay? Yeah. Change the control flow. Change. Yeah. So why you change? Yeah. For example, yeah. If you do not change, so think about this line is an instruction sequence. Instruction sequence. Okay? If you do not change the flow, you execute one after another in sequence, in its natural order. Okay? Yeah. But when one of the things happen here, in these 4 special cases, you jump to different location. Okay? You jump to different location. Yeah. How to specify this kind of location? Yes. So later we will see. So we have some specific way to tell, how to get to the right location. Yeah. So that is related to memory accesses. Related to the memory accesses. Yeah. Yeah. All right. Yeah. All right. Yeah. So let's look at the next question. Specify destination. Yeah. How to specify definition? When you jump, you need to get to some destination, right? But how do you provide expression of the destination? Yeah. So let's look at that. So the destination is specified explicitly in the instruction in the vast majority of cases. Yeah. Specified in the instruction. Yeah. Vast majority of the cases. Yeah. So that means in some very small situation, so not specified explicitly, okay, implicitly. Yeah, that's possible implicitly. Yeah, but vast majority, you need to specify. You need to provide a constant, right? Constant. So where to go? Yeah. So, yeah. All right. Procedure return being the major exception. Yes, for that exception, implicit case. Yeah, implicit case, that's the procedure return case. Yeah, the major exception. Yeah, since the return the target is not known at the compile time, it is very hard to specify where to return. Okay, so that location will be hidden. That location will be figured out at the runtime. At the runtime, yeah. All right. But here we just describe the general situation. Yeah. So here we will not go to very detailed along that direction. Yeah. All right. Yeah. Next, MIPS instruction format. So now we need to really look at the instruction format details. Yeah. Here I just give you high-level description. In the next video, I will show you the detailed format types. Yeah. All right. Encoding two addressing modes. Yeah. So here we go back to the previous slide. We need to use 1 bit. 1 bit. Why? Yeah, so 1 bit 0, 1 to encode two different addressing mode, immediate and displacement. Yeah, because they both belong to the same type, I type. How do you separate? 1 bit. Okay, 1 bit we can use to encode two addressing modes. Yeah. All right. So they can be encoded into opcode. Yeah, here. So there is this concept, opcode. The meaning is obvious. Operation. Operator. Operation. The code for the operation. Code for the operation. So opcode. So we have a specific code. Opcode. Later you will see 6 bits. We will use the first 6 bits of the instruction. We know total instruction 32 bits. In that 32 bits, the first 6 we use for the opcode. Yeah. Because we have that many, pretty much, yeah, for the type, for certain type, that many different operations we want to represent. So 100 something. So you can see 100 something. 128. Yeah. Actually 127, not 128. Why? Because the first one, 0, 0, 0, 0, 0, 0, there is one called this. It does not represent any operation. Now, it will be used in another type of instruction. We need this case. So it does not represent any operation. Yeah. So you can see up to 127 different operations we can represent using these 6 bits opcode. Yeah. All right. Fixed length instruction words. 32 bits. That's fixed length. each instruction word is 32-bit long. That's the property. Yeah. Okay. Yeah. So all instructions are 32-bit with a 6-bit primary output. Yeah. Here you can see primary opcode. When we say primary, that means there is secondary. There is a secondary code. But the secondary we do not call the opcode. Yeah. Later we will see another field. It's a secondary, similar to opcode. Yeah. But we do not call it opcode. We try to separate from opcode. We call it function field. That corresponds to the function. Yeah. So we will see. Yeah. In next video, we will see that. Yeah. Then, encoding a constant in a 16-bit field, immediate field. Encoding constant 16-bit immediate field. Yeah. All right. 2 cases for the displacement addressing case, like this. Yeah. Yeah. So this number, displacement, 16-bit field, immediate field. Okay. Then immediate constant for this case, also immediate field. Yeah. All right. Then the last case, yeah, also very special. That's called PC relative branch addresses. So what's that? Let me explain a little bit. Yeah. Here I use the branch instruction. Here I show you this branch instruction. Yeah. So what's the meaning here? B means branch. Okay. B means branch. EQ equal. In a branch we do comparison, right? So we compare 2 values. Okay. Yeah. Equal 0 or not. Do comparison. Yeah. EQ. Z means 0. Compare with 0. All right. So what do you compare? The value stored in R2 register is used to compare with the 0. If it's equal, then the branch returns true. The branch outcome is true. If it's not equal, the branch outcome is false. That's the meaning. Okay. All right. If it is true, target. What is the target? Target. Right. So your branch, conditional branch, you need to jump to a different location, right? The target means the target location, the target instruction, you need to jump to it. Okay. You need to jump to it. So that's the target. Yeah. All right. So here, what is the PC relative added to the PC address? So I need to explain that PC. PC means the program counter. Program counter. Okay. Program counter, what's that? What's that? It is a temporary register. In CPU, temporary register. Remember when we talk about regular registers, that's one type of register. Other than that, we have many other temporary registers. This PC is one of the temporary registers. What do we use for the PC? The PC is used to store the instruction, store the address of the next instruction. Yeah. So later we will learn that another time. Okay. Store the address of the next instruction, right? Yeah. Because you need to execute one instruction by one instruction. After you finish the current one, you need to get the next one, right? How do you fetch the next instruction? You need an address of that instruction, right? So the address is stored in the PC, temporary register. All right, so you have that. Now PC relative, yeah, you use the PC address as the base address. Then you jump certain number. So that number is specified in this target field. Target field store a constant. Displacement, you can understand as a displacement, right? Concept. Yeah. Now you need to jump from the base starting point stored in a PC, temporary register. So then you jump that many, so PC relative address. Finally, you will get address PC value plus the target displacement value. Together, you get your, next instruction address. Yeah. In that location, you can fetch the right instruction to be executed next. That's the meaning. Okay. So a lot of words to describe the situation. Yeah. All right. So let me finish our D.1 video here. Yeah. So you can see we covered a lot of things. Yeah. But something probably you cannot understand immediately, but later, many things we need to repeat several times. Many things we need to repeat many times. Yeah. All right, so let me stop here.